Welcome back, students. Let us complete section 1. Most of the topic I'm going to talk about here is going to be an optional topic. Okay, we talked about compound interest model and then its continuous version. And then we went through an example problem. Here's a model, and then for different n values, just calculate. And then backward problem. How long will it take to double? So basically solve an exponential equation for different equations with different n values. We went through both of those. One more thing here. It is possible to translate the different compounding scheme into just compounding once a year if the time frame is sufficiently long and then you measure it only precisely end of integer year. And that computation, that translation is called annual percentage yield. And that is used to compare different types of loans or savings. Basically, it's this. This is a compound interest model with different numbers of compounding. So n value can be various, typically 4 or 12, but it could be something else. But then again, what if I translate it so that compound only once a year? N value is 1, therefore we don't have denominator here, and then we just have t, not n times t, but we have different interest rate here. I'm using capital R. So what's the relationship between capital R and small r based upon the n value is the question. No sweat. Set those equal and then solve the equation. P cancel out, so we get that. And T cancel out. As a matter of fact, here, this one here, the left-hand side, is actually like this. And then compare now this t power and that t power. Remove those, and that's how you get this. So no more t either. And from this equation, third equation, solving for capital R, we get this. And this one is called APY, annual percentage yield, if it is expressed in terms of percentages. Want to see an example? Okay, here. Bank A offers an investment CD with annual interest rate of 5.1% compounded monthly. And that of Bank B offers an annual interest rate of 5.2% compounded quarterly. And Bank C offers investment CD with interest rate of 5.3%, but compounded only once a year, annually. Now, which bank gives you the best offer? That is the question. If you just look at the annual interest rate, 5.3% looks like the best. But as you saw before, if you compound more often, then money grows a little bit more quickly. So which is the best? Well, one good way to find out is to translate those into annual reinvest model, calculate this APY, and find out which is the best. Well, the computation is just this formula here. 1 plus 0.051 over 12 to the 12th power, and 1 plus 0.052 over 4 to the 4th power. Oh, never mind. So basically, we are comparing this 12, and then 5.1%. and then this is 4, 4, and then 5.2%, and then 1, 1, and then 5.3%. Calculate it and run your computation. And if you do it right, you're going to get 5.22 something, 5.302 something, and 5.3 precisely. So middle one here, quarterly reinvestment with 5.2% gives you the best rate. And how do you compare? One way to do that is to APY, annual percentage yield. Another way to do that is to go back to this model here and then calculate with arbitrary p and then compare. Okay, all right, we went through APY. Now let's go back to this original and let's discuss how in the world we get this formula at all. Ready? Okay, here's the proof. Now, at the end of each compounding period, interest will be added in. That's the idea. So initially we only have principal, but 1 month later or 1 quarter later, any one investment period later, it grows. Interest times the previous interest rate times the previous principal. So interest rate out of n times the previous principal. That much grew. And then let's use mathematics. Factor p out, and what do you get? We have p times this parenthesis 1 plus r over n multiplied there. And please remember this multiplication because this is going to be a recurring theme. Now, at the end of second month or second quarter or second compounding period, money grew a little bit more. Previous balance, which is this one as we calculated, plus the interest. Now, what is this interest? Interest rate of that period times the previous balance, which is this one. So R over n, that's the interest rate for the month, times previous principal. So that's common. And then previous principal is over here as well, so that's common. Factor it out, and what do you get? We have another 1 plus R over n. Do you see that? Entire thing is factored out. Here, that much is factored out, so you have, from here, everything is out, so we only have 1. And then here we have R over n, so we have 1 plus R over n again. So we get that squared. Do you see a pattern formation here? Let's do it again. After third month, or third quarter, or after third compounding period, previous balance plus some interest that grew, and the interest is given by interest rate times the previous balance of this. So this times R over n, right here. So previous times R over n, and then this previous balance here. So the common part, p times 1 plus R over n squared, that entire thing will be factored out. And then here, everything is out, so we have only 1. And here, we have R over n. So voila, again, 1 plus R over n coming out again. In the end, we have third power. See the pattern? Basically, each compounding is the multiplication of 1 plus R over n. And that is taking place how many times? For t years, so n times t months, n times t quarters, n times t compounding periods. And that's how we are going to get this exponential model. P times 1 plus R over n to the nt power. Did I say sketch of proof? Actually, this is a full proof. Because I said this ... maybe I felt a little bit uneasy about that, but it's just a repetition. We are not going to do mathematical induction here in this course. So we are done with those, and when n grows to infinity, basically you get natural exponential function showing up. Okay, those are pretty good theoretical background of this compound interest. But as for our applications of this compound interest model, we are not completely done yet. You see, if you have just a lot of money and then invest, that's good, but in many cases, you get into debt and you'll have to pay back. So the compound interest works backwards for you this time. And in that case, what do? And that's the last one here, installment payment model. I think it was Albert Einstein, who said about compound interest, those who know it earns it, those who don't pay it. Well, I understand compound interest, but believe me, I'm a mathematician. I know I teach this, but still I'm paying for this installment because I have mortgage here. I have no other choice. In Einstein's time, maybe, but nowadays everybody have to pay. So you gotta know how the payment applies, and it's a little bit more complicated. The formula is far more complicated. So A is monthly payment, and P is principal, and then is given by this formula where capital T is the total time period. For example, if you have 30-year mortgage, then capital T is 30. If you bought a house with 15-year mortgage, then capital T is 15. And most of those installment payments are done by monthly, so N is 12 all the time. Now, how in the world we are going to get this? Well, it goes kind of like this. So initially we have principal, so P, so that's my debt. Now, after 1 month, my debt grew by compounding P times 1 over R plus N. We discussed how in the world we did have this 1 plus R plus N keep being multiplied previously, so I'll take that for granted. But then again, out of this, I just paid for A, my monthly payment, done. So the difference is current balance. Okay, after another month later, this current balance grow by 1 plus R over N. You see, we discussed why in the world this thing is keeping multiplied before, okay? And then, okay, that was previous balance, so it grew. But then again, I just paid for a new money, A, second monthly payment. So the total, this one minus this times this, okay? And then let's do it again. This balance that grow, that's balance of my current debt, grows by this. We discussed it, 1 plus R over N. And then I just paid minus A. So if I just break apart, then this, and then bunch of subtractions. So basically what we have is this thing grows. We have this compound interest model that applies to debt. And then all these are my payment. Earlier payment, that actually grew as well. And then the effect of that grew as a matter of fact. And then next. And the most recent payment, no growth there. And then that should be equal to 0. And how do you find out this addition? And that's a bit long story, but it'll turn out that you can use this formula and then setting equal, flipping all the other to the other side, we can calculate my monthly payment like this. And then we can actually run this kind of thing with mortgage calculator or installment or car payments calculator. That thing is working like this. Again, it's a compound interest model. I'll stop here. This is getting way too complicated. So section 1 is done.